That old she's laying around somewhere yet? The old she's laying around. Yes. All right, we'll get started here. So again, about the tests, I will end out. So if you did submit your owl, and I see there was from a couple hours ago, I put a 0 in there. Get your attention, I got your attention, I got to be email and stuff like that. So I will go through OWL before the weekend's done, and I'll open up OWL on one screen and Canvas on the other. I'll fix it. So you got OWL done basically, or your percent looks like it's done, but I had a dash in this. I will fix that up this weekend. I will go through the tests yet and try to get those on. Those should be on before the weekend's done. So I'm still looking at those. Again, I got like 4 unknowns with 1 on its couple. So now I got the test back for the testing center. And now I need to match up the tests. And then I'll get those here. The asinine thing out of all that is the Scantron doesn't put the correct answer on. So I can't like hand you back your Scantron and your test because it doesn't put the correct answer on there. So I get this printer dump. I don't know what I'm going to do. I might have to take scissors and actually tape to each trying to hand it back. I don't know what yet. It's just not friendly. It's not friendly at all. The Scantrons I'm used to puts the correct answer to the right. If you got it wrong, it's no brainer. Then you just hand it back. There is not one correct answer on any of your Scantrons. But I get a computer dump. It's just not friendly. It's just not friendly. Okay, so we'll continue on here. Now, a couple things. I will continue to upload this to YouTube, but I have students that do this. So I've actually taken the YouTubes from a previous semester, and I've actually edited them so that I have them right here. If you wanted to actually look at it, do this before class to make it easier, you can actually view the YouTube and work these out so that when you come to class, you can just kind of look at it maybe a little bit better. And you would have it done. So here, this YouTube recording here would go to, you see the next recording, and the next recording is right here. So this would be a recording that does these 3 problems. So I really wouldn't have to throw this entire class out there in YouTube. I'm still going to do it because it does take me long to upload into my YouTube channel. But if you wanted to, or if you missed, it's all right here and it's already segmented off. So maybe that's something you want to do. Okay, so let's review where we left off. We are now doing stoichiometry. So what is stoichiometry? Well, first of all, you can write formulas of compounds. You know that this is magnesium chloride, and this is plus sodium hydroxide. And hopefully you would know that this is a double replacement reaction. And you can recognize that we have a double replacement reaction. And for that reaction, we want to put some numbers to it. How many grams of
sodium hydroxide would it take to react with magnesium chloride? Now it says enough. So we end up with 16 grams of magnesium hydroxide. So what is stoichiometry? It's putting numbers, usually mass, but it could be milliliters, it could be liters, grams, to reactions. It's just putting the numbers to reactions. Now, I use arrows and the mole ratio. You'll see the benefit of that if you've seen it previously. Teachers will say, we got to use 3 steps, but that's not true. So here will be my technique. Everything underneath will be in moles. Everything underneath will be in moles. I will put a rectangular box for the moles that I know for sure as my starting moles. Then I'm just going to draw an arrow, and we use the balanced equation to get the mole ratios. And in this case, we said we started out with 0.429 moles of aluminum. How many moles of iodine would we also need to react? Because there's 2 reactants, right? We got to have both reactants or there's no reaction that's going to take place. And when you want to figure out moles of something else, all you have to do is draw an arrow. And as soon as you point the arrow to the one you're looking for, that number from the balanced equation goes on top as a mole ratio. And what you're coming from goes on the bottom. So if I wanted to figure out my moles of aluminum iodide here, I would produce, I can draw an arrow from this that I know for sure is the correct moles. And my mole factor fraction would be 2 over 2. So this would also be 0.429. This is a much better way to do it because once you've got the moles given, you can do moles of the other ones right away. And you can always go moles back to grams. You can always go moles back to grams. So in this problem right here, we had 0.75 moles of propane, and we wanted to know how many moles of carbon dioxide we are going to produce. We draw our arrow this way, and when we draw our arrow this way to figure out the moles, this number here from the balanced equation is going to go on top, and we're going to have 3 over what we started with. There's a 1 there, 3 over 1. If we wanted to figure out our moles of water, we draw our arrow from the moles that we know, and then to get our mole factor fraction, it would be 4 over 1. So I'm just taking 0.75 times 4. Here I'm taking 0.75 times 3. So this method, we could figure out moles of oxygen. Much faster and easier to figure out moles of everything. And then you can always convert back to grams. So then we did this one where this is really, you're not given moles. Typically you're given grams. We're given 16 grams of magnesium hydroxide. The question is, how many moles of sodium hydroxide would have reacted? How many grams of sodium hydroxide would have reacted? Well, first thing we had to do was convert 16 grams of magnesium hydroxide to moles. Put our moles right there. We needed to figure out moles of sodium hydroxide. So we draw our arrow, and my mole factor fraction is 2 over 1. Once I have my moles of sodium hydroxide, I can go back to grams. That's what we did. Do not overthink this. Don't overthink this. Moles to grams, grams to moles. We know how to do that. All we're doing is draw an arrow to get our mole ratios. Our mole ratios. Okay. Let's do this one down here. It says what mass of oxygen gas from the air is consumed in the combustion of 702 grams of octane, C8H18, one of the principal components of gasoline. So we're given grams. I'm going to keep grams along the top. I'm only going to put moles underneath here. We need to calculate this in moles. Everything reacts according to moles. Unfortunately, we can't go 702 grams and say the ratio from grams is 25:2. It does not work that way. Everything has to be in moles. So the very first thing we're going to do is we are going to convert down here our 702 grams of C8H18. And down here, we're going to add these up. And hopefully you're going to remember that carbon is 12.01. Hydrogen is 1.01. So grab your calculator so the blood flows to the brain better when you're running your calculator. Get a head rush, run your calculator. So C8H18 should get us how many greens? Some vertical knots now. You ready? 114.26. 114.26 grams cancel out, right? This is just grams to moles, moles to grams. I'm going to draw my thing. Right there's my starting moles, right? Ooh, that's a fancy looking arrow. And my starting moles is 6.14, I believe. 6.14. Yes. 6.14. Once I have moles here, I can figure out moles of the other three. But I need to figure out moles of oxygen. So I'm going to draw this oval that I'm going to put my moles in. I'm going to draw an arrow like this because I need to calculate my moles here. And once I draw my arrow from the balanced equation, 25 would go on top. And my 2 is going to go on the bottom. 25/2. The mole ratio is 25:2. So you probably have this number in your calculator yet. Just take 25 divided by 2. We're going to get 76.8. So we're going to produce, or excuse me, we're going to consume 76.8 moles of oxygen. Now we just got to convert that back to grams, right? Back to grams. So we're going to go 1 mole of oxygen, 32 grams of oxygen, right? O2, 16.00. 16.00 times 2, because there's 2 oxygens, right? 32 there. If I take that. 3 sig figs, what do I get? If you keep your numbers, I think you get like 460. Okay, so 2460 grams of O2. So let's review how uncomplicated this is. We are going grams to moles. Molar mass, we're adding up 8 carbons and 18 hydrogens to get this number. This is always 1 mole. That is our starting moles. Once we have our starting moles, we can figure out moles of anything else. It was only asked for oxygen. We draw our arrow to figure out our moles of oxygen from the balanced equation. As soon as we point our arrow, it doesn't matter which way, our arrow can come from this side. It can come from here over to here. But as soon as I point my arrow for the one I want to figure out, look to the balanced equation, that number goes on top. What you're coming from goes on the bottom. That gets you moles to moles and then moles back to grams. All right, let's go to the next page. So I put this on here because this is something you can relate to and the numbers don't lie. Politically, I like to say that I can sit at the 50-yard line in politics these days, but everybody's in one end zone on the right or one end zone on the left. So this will kind of give you an idea of, is there climate change? What is the possibility of climate change? It's CO2. And these numbers here do not lie. So we're going to start with a 20-pound cylinder of propane. You know what a 20-pound white barbecue cylinder looks like. Everybody in here knows what that looks like. Yes? Okay. So my question is, if you burn a 20-pound cylinder of propane, how many pounds of carbon dioxide are you putting into the air? How many pounds of oxygen are you consuming from the air? And how many pounds of water do we get? You can all relate to that. And the numbers don't lie. So the very first thing we have to do is convert. And I already converted 20 pounds is 9,080 grams. You want that? We know that 1 pound is equal to 453.5924 grams. So right here, we need to get moles. Now I'm going to sneak it in right here because we're going to need a lot of room. We've got 9,080 grams of C3H8. That's simply propane. It's going to be a small sneak in there. So grab your calculator, or maybe you can do the mental math on this because we know this is 12.01 and 1.01. .11 grams. 44.11 grams. Yes, 44.11. Righty. So now, how many moles of propane do we have? We have 206. 206 moles. Nothing new there. We're just going grams to moles, moles to grams. Now, what I'm going to do is I'm going to figure out moles of everything else. I'm going to figure out moles of oxygen we're going to take out of the air. I'm going to figure out moles of carbon dioxide we're going to put into the air. And I'm going to figure out the moles of water we are going to produce. How am I going to do that? I'm simply going to draw my arrows. And for this one right here, what is my mole factor fraction? 5/1. Yes, 5/1. I'm going to draw my arrow here. It doesn't have to look pretty. And on this one, what is my mole factor fraction? 3/1. And I'm going to draw my arrow to here. And my mole factor fraction is 1. And if you grab your calculator and put those in, you're just multiplying this by 5. This is 1,030 moles. We multiply this by 3. We can do this in our head. We're going to get 618. And if we multiply this by 4, we're going to get 824, right? It's really simple to get moles of everything now. And once you have moles of everything, you can convert all those moles back to grams, right? So what do you think? Are you putting in more than 20 pounds of carbon dioxide into the air? Or less? The numbers aren't going to lie. Let's figure it out. Let's take our 1,000. Do this right here. We got 1,030 moles of O2. One mole of O2 . 32 grams of O2. So we could get grams out of this, but let's do our last step. You could stop right there to get grams. Let's actually go to pounds. So 453.5924 grams in 1 pound. And let's grab our calculator last. Let's do the next one. Let's take our CO2 and do it right here. We've got 618 mole of CO2. One mole of CO2. How many grams? 34.01 grams of CO2. And we can stop right here. You can put your gram answers and your pound answer. Drop down our other moles right here. We've got 618. No, I did that already. We've got 824. Water is 18.02 grams. Now let's grab our calculators, push those through. We can write our grams up here. We can stop right here and do our grams. We can write our grams in and their pounds, all the 3 sig figs. All the 3 sig figs would get us . $72.7 pounds of oxygen. $60 pounds of CO2, 60 pounds of carbon dioxide. $2.7 pounds, huh? Now, there is no ifs, ands, or buts. We are putting tons and tons and tons and tons of carbon dioxide into the air. This is one 20-pound cylinder. We're putting millions of tons into the air because if you live out in the country, you don't have a 20-pound cylinder. You got a great big silver tank, right? Have you seen the big silver tanks for burning propane? Yes. Then that doesn't include all the natural gas that comes in. What are we burning for natural gas? Carbon dioxide and water. So my friend that's in the right end zone, oh, that is wonderful. The carbon dioxide is wonderful. The trees and the plants love it. Are we planting more trees? Do we have more grass? Or are we putting in more parking lots and more homes and getting rid of trees and grass? Especially in the Amazon, right? We're not. We don't have more CO2 absorbers out there. So there is no ifs, ands, or buts. They've got core samples in the ice cap to measure how much CO2 is in the atmosphere hundreds of years ago. You just drill down into the ice from hundreds of years ago. There's no doubt we are putting tons and tons of CO2 into the air. Okay, the numbers do not lie. 20-pound cylinder, 60 pounds of carbon dioxide. The numbers just don't lie. Okay, let's go to the next section is on limiting reactants. So far, and for those of you that have done labs so far, you didn't worry about the HCl in lab. But we're going to talk about limiting reactants now. And let me page back. Because I have something like this. I have the word enough grams up here. Realize we calculated how many grams of sodium hydroxide we need. The reaction is not going to take place unless we have magnesium chloride to go with it, right? Down here, we have 702 grams of octane. We calculated that it would take 2,460 grams of oxygen. Now, when we burn fuel here and coming up, unless you're doing something crazy, like burning fuel or running an engine inside of a closed garage or a closed camper, you're not worried about running out of oxygen, right? But there are some reactions where we worry about which one runs out first. And that is your limiting, what we call the limiting reactant. It's going to limit how much you get per product. Now, this is how I introduced it. Think about this. I'm going to have to up my numbers. And for gender neutral, I'm going to change this problem too. But for now, 26 students in a class. You have 8 males and 18 females in the class of 26 students. Almost seems to be our college ratio coming up these days. For a class project, you want to form groups with 2 males, 3 females. How many groups can you make? Which is limiting? Which runs out first if you're making groups? And if you make groups and you can say, okay, 2 guys and 3 gals in this corner and 2 guys and 3 gals here and 2 guys and 3. When do you stop making groups? And how many groups can you make? So it's simply, here's my ratio, 2 males, 3 females make 1 group, right? How many groups? 4 groups. We are going to do this exactly the way we are going to do moles in reactions. Check this out. We have 8 males, agreed? Okay, this is what we have. My question to you is, using the mole ratio, how many females would you need to have all of those 8 males in a group? I'm just going to draw my arrow. What is my mole factor fraction? 3/2, right? So if I take 8 times 3, I get 24. 24 divided by 2 is 12. If I have a class of 20 students, of which 8 of them are males, 12 are females, everybody's going to end up in a group. Yes? Nobody's left over. There is nobody left over. However, I don't have 12. Down here, I'm going to put in exactly what I have. I don't know why I made that so big. I have 18. We are going to do the exact same thing with moles. When you get to this point and you say you have 12 moles of females and you have 8, you need 12 moles of females, excuse me. You need 12 moles of females, but you have 18 moles. Do you have enough females? Yeah, you have excess. You have excess, which means the males are limiting. The males are going to limit how many groups we can create, right? The males are going to limit how many groups we can make. Now, if I go back to the same thing, I can put three females, 2 males in this corner, and 3 females and 2 males in this corner, and so on. I would be done after I make 4 groups, right? But let's do that. Now listen, once you get to this point, everything is going to be in moles. to figure out your moles of product over here, you stop making groups when you run out of what you have of the limiting. Let me say that again. You are going to stop making groups, or you are going to stop making products on the right, when you run out of what you have of the limiting one. So all you do is come out of what you have of the limiting one, do the mole ratio step, which is 1 right there over 2, 8 divided by 2, 4 groups, right? It's exactly the same thing we are going to do. And then we could say, well, how many females are left over here? 6, right? There's going to be 6 left over. 6 excess. Let's do that down here. We're going to do the exact same thing. Again, this is called a limiting problem because in this case, you know it's limiting if you're given grams of both reactants. You have to be concerned of one of these running out first before the other. We do the exact same thing we just did. So we are going to calculate how many grams, how many moles here we have. So silicon nitride is a very hard, high temperature resistant ceramic used as a component of turbine blades and jet engines. It is prepared according to the following equation, which is limiting reactant. How many grams of product produced? From 2 grams of silicon and 1.5 grams of nitrogen. So we are going to calculate how many moles we have. We're going to evaluate how many moles we need. And then we're going to calculate here how many moles we have. Exactly what we did up above. So let's go right here. Let's get moles out of this. So we've got 2 grams of silicon. One mole, how many grams? Grab your periodic table, calculator. Get a head rush, use your calculator and your periodic table both. Blood flows to the brain using a calculator and a periodic table. So, right here. 28.09 looks like. 28.09. So we've got 28.09 grams of silicon in a mole. There's my starting moles. Sig figs, starting out with 2 sig figs here. Excuse me, 2 sig figs, 3 sig figs. 0.0712 moles, I think I'm starting out with. Now, draw our arrow. How many moles of nitrogen do we need? My mole factor fraction is 2/3, right? Just from the balanced equation, 2/3. So if I take what I have left in my calculator, 0.0712 multiplied by 2, divide by 3, I need 0.0475 moles of nitrogen. Well, let's figure out how many moles I actually have. It's right here. I have 1.50 grams of nitrogen. $14.01 for nitrogen from the periodic table, two sig fig, or excuse me, two decimal places. So 28.02. So it looks like I have 0.0535 moles. Yeah, just 1.5 divided by 28.02. Yes. Now you're just looking at these two numbers. Yes. You have too much. Yes. You have too much. So right away, this is going to be excess. This is going to be limiting. Now look at this. 2 grams is more than 1.5 grams, but your 2 grams is going to run out first. Some of your 1.5 grams is going to be left over. The reaction is going to stop making this product when you run out of your 2 grams of silicon. Right? The reaction is going to go, but when you run out of the 2 grams of silicon, your reaction's done. So the question is, how many moles of silicon nitride here are you going to make? How many moles are you going to make? Remember what I set up here. Come off of what you have of the limiting. It's either going to be this box or this box, right? So we know that this many moles here is all consumed. So we are going to draw an arrow. It doesn't matter where it goes. It can be ugly. I'm going to come out of this box. I'm going down below. No, I don't need to go down below. I'm going to go right between here because I got a different color. Right here. I come out of what I have of the limiting, and my mole ratio is 1/3, right? 1/3. So if I take my 0.0712, I am going to get 0.00237. Yes? Now, let me give you a hint as well. Multiple choice. Here's my multiple choice answers. A, 4.62 grams. B, 5.19 grams. C, 1.42 grams. D, 3.22 grams. There's only one number that is even possible. 3 out of these 4 you can cross out. First of all, if the ratio was perfect, using law of conservation of mass, you only have one product. If you react 2 grams with 1.5 grams, what's the most you can get? 3.5, right? The most we can get is 3.5. This is junk, and this is junk. Know that either 2 grams is going to be used up or 1.5 grams is going to be used up. So 1.42, that's way too low. That's not even possible, right? This is the only answer that makes any sense. I don't know if that's the answer. I just made it up. So make sure you're considering the law of conservation of mass and matter, which we are going to do in our next problem. So let's figure out what it is. We've got 0.0237 mole of SiN4. One mole is, Si3. Get a 3 in. Jeez. I think I do have COVID brain after all. I've said so many things wrong. And I'm just going to use that excuse the rest of my life. COVID brain and getting kicked in the head by a cow. Those are my 2. I use getting kicked in the head by a cow up until now. I can go to COVID brain. Man, I've said some things wrong today. I just did a survey last night. COVID memory loss. I guess maybe I better change my answer. Grams. Grams of Si3N4 is 140.31, 140.31, 140.31, 140.31. All right, thank you. Moles cancel out. And if I multiply that out, I get 3.33. Now let's talk about this before we turn the page and do one. 3.33 grams here came from 2 grams here. How many grams of the 1.50 grams are left over? How many grams of the 1.50 grams are left over? .17, right? 0.17. I produced 3.33 grams. Where did it come from? 2 grams come from here. The most you can get is 3.5 grams, right? How short am I from 3.5 grams? 0.17 grams. All right, the next problem is going to put everything together. Everything. So in a single replacement reaction, 53.34 grams of aluminum bromide is reacted with 19.00 grams of fluorine. And we just got to figure out every letter here. And so I put the atomic masses up here. Atomic weights 26.98 for aluminum, fluorine 19.00, and bromine 79.9. So that's kind of nice. Okay. Now we are doing the exact same thing. we are going to calculate how many moles right here we have. We're going to calculate how many moles of fluorine we need. And we're going to calculate how many moles we have of it. Once we get that evaluated, we can figure out which one's limiting and which one's in excess. Right? So letter A is, how many moles of aluminum bromide do you have? So we'll calculate it out right here. That's where I left room. We have 53.34 grams bromide. Grams to moles. Grams to moles. Grams to moles, moles to grams. Everybody's calculated this out? $266.68. That's 266.68 grams cancel out. So then if we divide this out, we would get to 4 sig figs. We are going to get 0.2000, I believe, mole of aluminum bromide to 3 sig figs. Yes? So we can go up here and put this in. 0.2000 moles of aluminum bromide. Let's draw our arrow to figure out how many moles of fluorine we need to use all of this up. How many moles of fluorine do we need? The mole ratio is 3/2, right? 3/2. So we need, well, 0.3. So the next logical question is, how many moles of fluorine do we have? We're going to take our 19 grams to see if it's higher or lower than this, right? We're going to take our 19 grams. If it's higher than the 0.3 moles, it's in excess. If it's lower, this one's going to be limited. So we answered B. How many moles of fluorine needed? This right here, I guess I'll put at the end of this is 0.3000 mole of fluorine. So how many moles of fluorine do you have? We've got 19.00 grams of fluorine. Zoom. Oh, well, fluorine's 19, but there's 2 of them. So 38. So 0.5000 mole. So we can go up here and put that in. They're canceling out. I'm happy about that. I have do we have enough? Do we have too much? We got too much, right? This is going to be in excess. It's not always this one's in excess. This is just how they're coming out. This one can be limiting. It doesn't, I could have put the fluorine here first, right? In this reaction. So please don't think that the first one's always limiting, the second one's in excess. We know that this is limiting. Well, look at this. This reaction is going to stop when the 53.34 grams of aluminum bromide is used up, right? You would think it's 19 grams. 19 grams is much smaller than this, but it doesn't work that way. Everything reacts according to the mole ratios. Right? So which one is limiting here is AlBr3. Which reactant in excess F2. How many moles of the reactant in excess are left over? Well, we can do it right here, right? We have 0.5. We've got 0.5. We've got 0.2000 excess. 0.2 moles of excess, right? Down here we have 5,000 mole minus what we needed, which was 0.300 moles. 2,000 F2 excess. Well, how many grams of the reactant in excess are left over? 0.2 moles. And we've got this number up above, 1 mole of fluorine. Grams. Still at 4 sig figs so far. So 7, 6, 0 grams of fluorine. Left over. Excess, right? So the next question, how many moles of each product, aluminum fluoride and bromine, are produced? So we're going to do the same thing. We're going up above to the reaction. Figure that out. This is the moles of both products. So we're going to go up here. We're going to draw ovals because we're going to put moles there. This is determined by the limiting one that runs out, right? You are drawing your arrow from either this box or this box, whichever one has limiting written up there, correct? It's not always this one. So let's draw that thing. We're going down here. What's my mole factor fraction for this one? 2/2. So I'm going to produce, it's the same number then, 0.2 moles here. And I'll just do this, it might make it look a little bit better. My mole factor fraction here is 3/2, right? 3/2. Three over two is going to get me 0.3000. Okay, so let me write this down here. So we're going to finish calculating down here. So we've got 2,000 mole of aluminum chloride and 0.300. Now, how many grams of bromine gas produced? There's our moles, right? 0.300. And then one mole of bromine. Grams of bromine. So 79.9 times 2. $59.80. Out to 4 sig figs again, 47. Point 4. $47.94. Okay. Next one, and we're going to make sure these make sense. Grams of aluminum fluoride produced. So 1 aluminum, 3 fluorides. I think we get this. 0.98, I think. 4 sig figs. 18.80. But now, as my daughter would say, I'm so excited. I am so excited to show you this. Watch this now. Watch this. This is my total grams of product produced if I add these up, right? All right. Here comes a cool looking arrow. See if you can match my cool looking arrow. Oh yeah. That's sweet. Bob Ross got nothing on me. Now, this is my total product. If I add those together, I get 64.74 grams. That's my total grams of product I produce. That better match. The question is, does this match my total grams of reactant that reacted? My total grams of reactants, plural, that reacted. Well, let's go back up here. Going into this 64.74 grams is the 53.34 grams of limiting's gone, correct? This is consumed. 53.34 grams is consumed, yes? Well, let's go down here. And I know that down here, 53.34 grams. This is my aluminum bromide that was limited. So for sure, that's all consumed. Plus, how many grams? Let's talk about my fluorine. My excess fluorine. How many grams did I start with? Started with 19.00 grams. Right? 19 grams. Let's subtract how much did we have excess that we calculated? Excess. Left over. We calculated what? $7.600 grams, yes? Jeez, I need to put grams in all of this. That means if I take 19 minus 7.6, the amount that reacted was 11.40 grams. And then does the 53.34 grams plus the 11.40 grams, that is 64.74. Heck yeah, right? This refrigerator art, get ready for Thanksgiving's coming up. You take this page, put it on your refrigerator when your relatives come. I want them to ask what this is. Tell them it's science. There's been an attack on science lately and you respect science. So this should be your refrigerator art for Thanksgiving. So let me give you some quiz questions to refine all of this. So the quiz question is going to be some stoichiometry. It's going to be drawing some arrows. Try to do 1 through 10 on this take-home quiz. Work on some owl. There's maybe a deadline out there, an owl. I need to back off, huh? So chapter 4, part 1. Does anybody know when that owl deadline is? Sunday? Yeah, that's not going to be well, maybe it is. No, because we're not there yet. I'll probably back that off. No, yeah, we need to back that off because we need to get to page 5. So I'll back that off. So Sunday, I'll change that. I'll go through all this weekend. I'll submit everything, clean it all up in the Canvas. I'll try to get the tests all figured out. Figure out a way to get it back to you. So. If you have trouble,